So today I want to talk to you about the Bohr model of the hydrogen atom. So first, meet Niels Bohr. He was a Danish physicist and an active participant in the early development of quantum mechanics. And in 1913 he published his model of the hydrogen atom, where he provided an explanation of the atomic spectra that had been seen by others, Balmer, Lyman, Paschen, Brackett, and Pfund, and includes some features of the currently accepted theory. His model includes both classical and non-classical ideas. Often it's called the semi-classical model. And what he did was he applied Planck's ideas of quantized energy levels to the orbiting electrons in the atom. Now, for this work, he was awarded the 1922 Nobel Prize in Physics for structure of atoms and the radiation emitting from them. Now, it's interesting to note that not only did Bohr have a huge list of accomplishments of his own, but you could probably also add being a great parent to that list. He had 3 sons. One was a medical doctor, one was a lawyer who was also an Olympic athlete, and one won the Nobel Prize in Physics in the 1950s for his work on nuclear theory. So, you know, quite a successful family. Now, before I get started on talking about all the ins and outs of this model, you should know that this model is now considered obsolete. But we still teach it, okay? The reason that we still teach it is because it provides a nice conceptual framework for the model that we now know is correct, which is the probabilistic quantum mechanical theory. It can still be used, however, to understand angular momentum quantization and energy quantization when you apply to atomic-sized systems. But you should be aware that this sort of semi-classical planetary model of the atom, which I'm getting ready to tell you about, has been replaced by the probabilistic electron cloud model that quantum mechanics says is true. Okay? But with that, on with the show. So, Bohr's model says that you have a planetary kind of model where you have your proton in the center, and it's sort of similar to the sun. And then you have your electron orbiting that proton, kind of like the planets do the sun. Now, the centripetal force that's necessary for this orbit is provided by the Coulomb attraction between the positively charged nucleus and the negatively charged electron. And the equation for that is mv squared over r, which is the centripetal force, is equal to 1 over 4 pi epsilon naught e squared over r squared. Here I'm just setting the magnitudes equal. Now 1 over 4 pi epsilon naught is also the Coulomb constant, k, where k is 8.99 times 10 to the 9th. Epsilon naught is the permittivity of free space, which is 8.854 times 10 to the minus 12 in SI units. E is the charge on the electron, 1.602 times 10 to the minus 19 coulombs, and r is the radius. The m here, the mass, is the mass of the object in orbit, which is here the electron, with a mass of 9.11 times 10 to the minus 31 kilograms. Now, this wasn't the first planetary model of the atom that was proposed. Rutherford had also proposed a planetary model, based on his results of tinfoil experiments, which led him to believe that the nucleus was a very small, dense, positively charged body. Okay? However, everyone understood that Rutherford's model was flawed. And the reason that Rutherford's model was flawed was because your electrons are charged particles, and they're moving in circular orbits. And of course, we know that circles mean that you're constantly accelerating. And it was also known that accelerating charges radiate. And so what would happen, as physicists knew at the time, was that the electron would orbit, and because it was making a circle, it would radiate away some of its energy as it continued in that orbit, losing energy until it eventually spiraled in and crashed into the nucleus. And there wasn't really a good successful explanation for why this wasn't happening. Okay? So what Bohr said in his model was, look, there's certain electron orbits, and those orbits are stable. And in those orbits, the electrons do not radiate away their energy due to the fact that accelerated charges usually radiate. And that would mean that the energy of the atom remains constant, and classical mechanics can be used to describe the electron's motion. The same kind of physics, in other words, that describes the orbits of the planets around the sun can be used to describe what's going on between an electron and a proton in a hydrogen atom. Okay? Okay, now, which orbits work? Well, he said that the allowed electron orbits are determined by a condition imposed on the angular momenta of the electron's orbit. Okay? So the allowed orbits are those for which the electron's orbital angular momentum around the nucleus is quantized and equal to an integer multiple of h bar, which is Planck's constant divided by 2 pi. Now, in a circle, L is equal to mvr. Normally, we write L is equal to r cross p, the cross product of the radius vector and the momentum. But in a circle, those always move at right angles, and so we can rewrite the magnitude of L as mvr, the mass times the velocity times the radius. And then you would set that equal, mvr equals nh bar, or nh over 2 pi. And those orbits are the ones that would be stable in the electron. Now we can do a little math to this. If you combine that equation, that the angular momentum is equal to mvr is equal to nh bar, and you combine that with the equation for the centripetal force, mv squared over r is equal to 1 over 4 pi epsilon naught e squared over r squared, let's just do a little manipulation of that equation. First of all, in the equation for the centripetal force, let's cross multiply those radii. So if I take that r squared cross multiply it, I get mv squared r squared. And if I take the 1 over r on the left-hand side and cross multiply it, then I end up with 1 over 4 pi epsilon naught e squared times r. Now let's just multiply both sides of that equation by another mass. So you have m squared v squared r squared is equal to m over 4 pi epsilon naught e squared times r. Well, m squared v squared r squared is just the angular momentum squared, which means that you should be able to set that equation equal to nh bar squared. Now I can rearrange that equation and solve for r. When I do that, I get r is equal to n squared h bar squared 4 pi epsilon naught divided by m e squared. Those are all known fundamental constants. H bar, Planck's constant divided by 2 pi, epsilon naught, the permittivity of free space, the mass and charge of the electron. So if you multiply all those things together, figure out what you get something called the Bohr radius. This is a naught, often indicated as a naught in textbooks, and the number is 5.3 times 10 to the minus 11 meters. And so we end up with radii that are integer multiples squared of the Bohr radius, 5.3 times 10 to the minus 11 meters. And so this shows that the radii of the allowed orbits have discrete values. In other words, the distance from the proton to the electron's orbit is fixed, okay, quantized, and only allowed to have certain values. Now, within these orbits, how fast is the electron moving? Is this a relativistic speed? So let's solve for how fast the electron's moving in the first excited state with n equal to 2, and determine whether or not those are relativistic speeds. So if we do this, then we have L is equal to mvr is equal to nh bar. So I'm going to rearrange that equation and solve for my velocity. V is equal to nh bar over mr. And now I'm going to plug in for what r is for the n equal to 2 level. So what I would have then is r is equal to n squared a naught. One of the n's on the top and the bottom would cancel, leaving me with an equation for the speeds, h bar over m n a naught, and these would be the speeds for any given orbit. If I plug in the values of those constants for n equal to 2 and solve for my speed, I get 1.1 times 10 to the 6 meters per second. Now, since the speed of light is 3 times 10 to the 8 meters per second, this means that the speeds of my electrons in their orbits around the proton are less than 1% of the speed of light. Note that, it's proportional to 1 over n, so the speeds are only going to drop as n increases. As you go up in energy level, the electrons will get slower and slower, and so they never really approach the speed of light at all. So they're non-relativistic. So just to remind you, one of the things that made Schrödinger decide he wanted to go ahead and publish his non-relativistic equation in quantum mechanics was that he knew that he could solve for the hydrogen atom's electrons because they were non-relativistic, and so was his equation. So it all worked out. Now, radiation is emitted by that electron when it makes a transition from a more energetic initial state to a lower energy orbit. We can't treat this classically, okay? So this is a very non-classical idea. Remember, this was published in 1913, so it was still a kind of a new thing that you even had this change in energy giving a discretized value of the photon energy. And so what he said was, if we can solve for what the energy initially and finally of that electron is, and then make a difference, then the energy should be conserved. So if the initial energy state is higher than the final, then a photon would be emitted. And the frequency of that emitted photon would be hf from the equation for the delta E. Now, if an electron wanted to jump up a level, it had to receive that amount of energy, oftentimes in the form of a photon, to make that jump. So let's solve for what these energies would be. Remember that Bohr said that we could treat these things classically. We could use classical techniques. Well, the mechanical energy of an object is the sum of its kinetic plus its potential energies. That would be classically 1/2 mv squared plus the Coulomb energy, okay? So the Coulomb equation for the potential energy is negative 1/4 pi epsilon naught E squared over R. The negative sign comes from the fact that you have two charges, one plus E and one minus E, and so when you multiply those together, it gives you a negative sign. Now we can go back to the equation for the centripetal force, mv squared over R equals 1/4 pi epsilon naught E squared over R squared. So the mv squared in there, we can just multiply both sides by R and figure out what 1/2 mv squared is if we multiply both sides of the equation by 1/2. And it ends up that it's 1/2 times 1/4 pi epsilon naught E squared over R. If I plug that in for 1/2 mv squared, then my total energy is negative 1/2 times 1/4 pi epsilon naught E squared over R. So that's my total energy for the system. Now this energy is negative, and what that means is that the electron is bound to the proton. In other words, you would have to give it energy in order to free it from the proton, in order to break that bond, if you will, in between the electron and the proton. So we now have the equation for the radius, which is n squared times a naught, and we can plug that into our equation for the energy. And if we do that, the energy of any orbit becomes negative 1/2 times 1/4 pi epsilon naught E squared over n squared a naught. Now solving for all the constants in that equation, multiplying the 1/2 times the 1/4 pi epsilon naught times the E squared over a naught, you end up with an energy of negative 13.6 eV. This is for the ground state where n is equal to 1. And for any other state, the energy would be negative 13.6 eV divided by n squared, where n is your energy level. So this gives you the energy levels for the electrons in the Bohr atom. Now, a great triumph of the Bohr model of the atom is that it accurately described what was going on with hydrogen spectra. So let me explain here. The Balmer series corresponds to a higher energy state making a transition to the first excited state where n is equal to 2. That gives you the Balmer series with visible light. If you're making a transition from a higher energy state to the ground state, n equal to 1, that gives you your ultraviolet series or your Lyman series. And then the Paschen, Brackett, and Pfund could be when you have a transition from a higher energy state to the n equal to 3, 4, or 5 state, depending on which one you're talking about. And these are energies that correspond to the infrared region of the electromagnetic spectrum. Okay? Now, an ionization energy is the amount of energy that's needed to completely remove the electron from the ground state of the atom. And that would be, for the ground state, 13.6 eV. So in other words, you just take the absolute value of the binding energy to get the ionization energy. Now, Bohr's explanation of this led to an explanation for the equations that I showed you in the previous lecture that Redbird wrote in his form. Okay? So if you assume that a change in energy level is caused by a photon, then you can have EI minus EF is equal to HF. Rearranging and solving for the frequency in that equation, I have the frequency is equal to the energy difference divided by Planck's constant. Now, if I use the equation that I've developed for the Coulomb energy that we derive from the Coulomb energy techniques for the electron in the hydrogen atom in the Bohr model, then you end up with the frequency is equal to Ke squared over 2a0h times 1 over n final squared minus 1 over n initial squared. Remember, Ke here is the Coulomb constant, which is 1/4 pi epsilon naught, just using a little bit of shorthand here. Okay? Now, 1 over n final squared is the final energy state in the energy level, and 1 over n initial squared is the initial energy level. Okay? Now, remember, we had in our previous lecture for the Redbird model, we had it written in terms of what the wavelength was. So if we look at that instead, Remember, we can use c is equal to lambda f to solve for what the wavelength is. And if we rewrite our equation now in terms of 1 over the wavelength, we're just dividing your frequency by c. And then we have k e squared over 2a naught hc times 1 over n final squared minus 1 over n initial squared, or n or m or whatever you want to call your energy levels, okay? And if we take this constant k e squared over 2a naught hc and multiply all those constants together, then we get 1.097 times 10 to the 7th inverse meters. And this is the Redbird constant, okay? So Bohr's model successfully explained why the hydrogen spectra look the way that they do, and why Rydberg's equation worked for the fit. So it explained the physics behind the hydrogen spectra that people had been trying to figure out for so long. And this was considered a great triumph for the model, and why he won the 1922 Nobel Prize. Now, the remaining question was still, why are certain orbits stable and why are certain orbits not stable? In other words, we know from looking at the model that r is equal to n squared a naught, but why is that? Okay? Well, this was published in 1913, Bohr's Model. And remember that just a couple of years later, de Broglie published his equation for matter waves and their wavelength, where lambda is equal to h over p. So the explanation is this, according to de Broglie and Bohr, that a confined wave, a confined matter wave, will become a standing wave, and all other possible wavelengths will be canceled out through destructive interference. So if you look at Bohr's quantization condition, mvr is equal to nh bar, and you just do a little rearranging, you get r is equal to nh bar over mv, and then if you remember that h bar is h over 2 pi, and then multiply by 2 pi on both sides, then you have 2 pi r, which is the circumference of that orbit, is equal to nh over mv. Well, now this is non-relativistic speeds, so h over mv is equal to h over p, which is the de Broglie wavelength. And so what you're saying here is that 2 pi r is equal to n lambda. In other words, the orbit, the circumference of that path, will be integer multiples of the de Broglie wavelength. And that's the same thing as the equation for standing waves, okay? So, with the combination of Bohr's explanation and de Broglie's wavelength for the matter waves, you now have sort of an explanation for why only certain orbits are okay. It's the ones that form standing waves for these electron orbits, okay? And that's also why it wouldn't decay, right? Once it's in an orbit, if it tried to lose a little bit of energy, there'd be destructive interference, and it wouldn't be able to lose that energy because the standing wave would die. Now you can also extend this to other atoms, but only so far. The Bohr model only works for single electron atoms. When you have multiple electrons, then in your potential energy function, you would have to start considering the Coulomb repulsion between electrons. And that's one of the main failings of the Bohr model, that it really can't be extended to pretty much any atom that doesn't have more than one electron, which is most atoms, okay? But he did successfully extend his model to other elements that were ionized, for example. So if you have an atom that's lost all but one of its electrons, then you can just redo the derivation that we just did for Bohr's model of the atom. You take your centripetal force, mv squared over r, and set it equal to the Coulomb force. In this case, when you multiply the two charges together between the nucleus and the electron, then the nuclear charge would be z times e, where z is the atomic number of that element, and that would give you the number of protons in the nucleus, right? So for example, if you were looking at lithium that had been ionized 2 times and only had one remaining electron, then you would have 3 protons. And so the charge, when you multiply 3e times e, you'd get 3e squared, okay? If you do that, and you follow through on that derivation, then you find that the equation for the radii is altered slightly. The new equation for the radius would be n squared times a naught divided by z, that atomic number. And the energy levels would be minus 13.6 eV times z squared over n squared, okay, where you're squaring the atomic number and dividing by the energy level squared. So for example, what would be the ionization energy for the electron in triply ionized beryllium? And what's the radius of that ground state orbit? So using these equations, r is equal to n squared a naught over z, if n is equal to 1, then you just have 1 times the Bohr radius, 5.3 times 10 to the minus 11 meters, divided by the atomic number for beryllium, which is 4. And then you end up with a radius of 1.3 times 10 to the minus 11 meters. What this means, of course, is that because of the increased charge of the nucleus, that there's a stronger Coulomb attraction in between the nucleus and the electron, which pulls that electron in closer towards the nucleus than it was before. Now, if you want to solve for what the ionization energy is, we're going to use our equation for the energy levels. So here we have minus 13.6 eV times z squared divided by n squared. Here z is equal to 4 and n is equal to 1. And so we have 16 times minus 13.6 eV, which gives us minus 217.6 electron volts. Now the ionization energy is the absolute value of that. It's the amount of energy that it takes to remove that electron, the amount of energy that you have to give. And so the ionization energy would be 217.6 eV. All right. Well, that's kind of a lot of information to take in. I'll see you in class. Remember, you can always pause me if you need a little extra time or help, and I'll be happy to answer any questions you might have. Thanks. Bye.